Yeah, so welcome everyone to this afternoon session of Staggered Day today, the third lecture by Tom Hutchcroft. So over to you, Tom.
Great. Thanks everyone for coming again. So just to recap what we did last time, well, we did a few things. We looked at the PC versus PU problem and this strengthened reformulation in terms of operator norms, the PC less than P22, and we showed that if you have spectral radius smaller than a half, that's a sufficient condition for PC less than P22, and in particular, we deduced that every non-amenable group has at least one K-graph of the conjecturist group. And we looked at mean field critical behavior and all that stuff as well. Okay. And just at the end, we had this proof that you can't have a unique infinite cluster at criticality on any transitive graph of exponential growth. And remember that worked by looking at this quantity P of n, which is the minimal connection probability between points at distance at most n. And we showed that that always decays at least like the growth of the graph to the minus n, but the growth is defined as this lim sup. In fact, it's a limit, it's lim sup, which is the exponential growth of the graph. Okay. So what I want to tell you about today is, so again, as I said last time, we conjecture that in all sufficiently high dimensional settings, and non-amenable in this context is as high dimensional as it gets, we ought to have mean field critical behaviors. So critical percolation should look, for most intents and purposes, like a critical branching random walk. So in particular, the probability that you have volume at least n in the cluster at the origin should be like 1 over root n, the same as the progeny of the total progeny of a critical branching process. Okay. And as I said before, we don't know how to prove that, although we did show that if you have spectral radius less than half stay, then those things are true. It's discussed. So what I want to tell you about today is the proof of the best thing that we can prove in this direction, which is that you always have power law upper bounds. And so in particular, if we have any, so I'm going to assume unimodularity. Again, in the non-unimodular case, we actually understand much better than we completely understand everything. But the unimodular case, which includes K-graphs, is the one that's actually seems to be harder. So G is a unimodular transitive graph, and it has degree K and growth, and it has exponential volume growth, let's say bigger than some G, which is bigger than 1. Then there exist constants that only depend on the degree and on the growth, such that you have this polynomial, this power law found on the tail of the volume of the cluster at criticality. Okay. Now, the reason why I've stressed that these constants only depend on the growth and the degree is that this theorem has a nice corollary of resolving what's called Schramm's locality conjecture for PC in the exponential growth case. But before telling you about the proof of this theorem, I want to briefly talk about this conjecture because it's a really nice conjecture and explain how we deduce that the conjecture is true in the exponential growth case from this theorem. And so what the conjecture says is that if you have any sequence of transitive graphs Gn that converge locally to some other transitive graph G, so remember this local convergence is the same as we've seen in Mikloch's course. It means that eventually balls of radius R look the same in Gn as in G for any fixed R. Okay? So the locality conjecture says that if Gn converges locally to G and the Gn's all have PC less than 1, then PC of Gn converges to PC of G. Right? So in other words, given this global condition that PC is less than 1, the value of PC should be continuous with respect to the local quality. So it should, the critical probability should depend only on the local geometry of the graph, not on the global geometry, at least provided we have this condition that PC is less than 1. Because otherwise, for example, you could approximate an infinite transitive graph by finite transitive graphs that kind of have PC equal to 1, or maybe things that look like Z times a finite graph that are infinite but have PC equal to 1. And this is something you can kind of easily do that show that this continuity is not going to hold without this condition. And as I said, a corollary of this theorem, and really the important thing is here that the constants only depend on the degree and the growth, is that the locality conjecture is true, provided that all the graphs that you're looking at have exponential growth and the growth rate's bounded away from 1. Okay, so if there exists g strictly bigger than 1, so that the growths are all bigger than g, then the locality conjecture holds. Okay, so let's briefly explain why this is. And so first of all, there's a nice observation due to Gabor-Pete, which shows that PC is always lower semi-continuous. So PC of the limit graph is always bounded from above by the limits of the PCs in the sequence. Okay, and why is this true? Well, we saw, if you remember, when we proved the sharpness of the phase transition, like when we proved that when you're below PC, you have finite expected volume. If you remember, we defined this alternative parameter P tilde C, and we showed that you have finite expected volume below P tilde C, and you have an infinite cluster above P tilde C. So P tilde C must actually be equal to PC. But the proof of the bit above PC was actually quantitative, and it gave this plan that when you're epsilon above PC, you have the probability that the origin is an infinite cluster is at least this number, which is at least epsilon. Okay? And this bound holds uniformly, right? This is really, there are no hidden constants here. This is a totally uniform bound for every transitive graph. Okay? And a consequence of this is that let's say Rn is the radius up to which Gn and G coincide. So the balls are isomorphic. And so the local convergence exactly means that Rn is tending to infinity as n goes to infinity. Okay, well, we know that suppose we're epsilon above whatever PC of Gn is, right? But I'm going to look at percolation on G, but at this parameter defined in terms of PC of Gn. Okay, now, and suppose I look at the probability that the volume of the cluster of the origin is at least Rn. Well, G and Gn coincide up to radius R, right? So I can couple percolation on G and Gn so that they do the same thing inside this ball, right? And trivially, if the cluster is infinite in Gn, then it must have size at least Rn in G, because it's going to reach the boundary of this ball, right? And they're the same inside the ball. Okay, so I get this inequality. And then from this sharpness thing, I get that this is at least epsilon. Okay. So it follows that if P is really larger than this lim by some epsilon, right, then I can take the limit here. These Rn's are tending to infinity. So what I get is that in G, that the probability of being in an infinite cluster is at least epsilon. Okay. So in other words, what this is saying is that if you're really above the limits, then you're supercritical in G, and this is exactly the semi-continuity statement. So the point here is that this uniform lower bound on what's on the density at in slightly supercritical percolation is giving us this lower semi-continuity. And so to complete the proof in the exponential growth case, we need to go the other way. So we need to prove that if P is smaller than the limits, then it must actually be subcritical in G. Right? So what I might have that I want to rule out is that I have some P which is subcritical for all the GNs, and it's really very subcritical, so it's bounded away from their PCs, but it's supercritical in G. which of course might happen if the GMs are just finite or something like that. So you might have a big torus, and depending on how you define it, PC might be something else, but you're certainly never going to have an infinite cluster in a torus, but PC will be converging to PC. Sorry, but the infinite lattice has an infinite cluster of its PC. We want to rule out something like that. So here's how we'll do it. So it suffices to prove this quantitative claim that PC of GM is bounded above by PC of G plus, well, we just need something going to 0 as m goes to infinity. In fact, we'll prove this power law on the end. Okay? Where again, this is the radius that they agree up to. Okay? Well, we have by the theorem that there exists some constants so that the probability of having a large cluster in GM is always bounded by n to the this power law thing, provided p is smaller than or equal to PC of GM. Okay. So what that means is, well, if this inequality didn't hold, so we had PC of GM was bigger than PC of G plus epsilon, where epsilon is this, right? Then what we would get is that, well, this number would be smaller than PC of GM, so we could apply this inequality at this parameter. We get that the probability that the cluster has size at least r would be bounded by this this thing c r to the minus c, right? But as we saw before, you know, these two graphs are coinciding up to radius r, so this probability has to be at least the probability that you have an infinite cluster in G at the same parameter, right? But that's at least epsilon by sharpness again. Okay, and the point is, if epsilon is strictly larger than this power law, then we just get a contradiction. Okay, so we must have this inequality as claimed. So this gives us the whole thing. We're getting so Pette's argument gives one side and this gives the other side. And the general principle here is that if you have any uniform control of critical or near critical percolation for some class of graphs where you really need sort of an upper bound on something, then this is going to give you locality for that class. Okay, and one thing to note here is that you don't need to prove that there aren't infinite clusters in the class. So, for example, if you could prove something like this is just just an example of the kind of thing one might try to prove. Suppose you could prove that for every value of the degree, there's a constant, so that if you have any transitive graph with degrees bounded by k, and you look at the expected size of the cluster at PC minus epsilon, then it's bounded by, you know, this is totally arbitrary, c to the t to the t to the 1 over epsilon. Okay? But again, this is just an arbitrary function. If you can prove that there's any function of epsilon which works uniformly for all graphs, then you will have proven the locality conjecture. Okay? Because you can basically run almost the same elements I just showed you. So any uniform control of, say, this slightly subcritical population, well, this wouldn't even tell you that there are no infinite clusters at criticality. It's just saying that the phase transition is not blowing up too badly. This would suffice to prove locality. And in fact, locality is really equivalent to the existence of such a uniform control. It's just a compactness argument. Okay. Okay, cool. So what I want to do next is explain the proof of this power law upper bound for the transitive graphs of exponential growth. Okay. And ultimately, this is going to be rooted in a method of Eisenman, Keston, and Newman. So as I mentioned a while ago, well, what were Eisenman, Kester, and Newman actually doing in their paper? They were proving that there's at most one infinite cluster in supercritical percolation on ZD. Right. And of course, 2 years after their paper, Burton and King came along with their much simpler, more conceptual proof, which is the one everybody learns. But the Eisenman, Kester, Newman proof is very interesting. It actually gives much stronger quantitative information. Like, so this is really only implicit in their paper, but implicitly they establish the following fact, that if you do percolation on a box in ZD, and you look at an edge in the middle of the box, and you say, what's the probability that the endpoints of this edge belong to different clusters, each of which reaches the boundary of the box? Okay? And they prove that this is bounded by a constant times log n over root n. Okay, and again, this is only implicit in their work, but the method establishes this bound. The modern interest in this and people really looking at these quantitative things really comes from the work of Raphael Cerf in 2013, who sort of gave this bound, popularized this method, and also showed that you can strengthen it to get various slightly stronger powers of n and stuff like that on ZD. It's very interesting. So the proof of this is also, so by the way, of course, if you prove this bound, it follows that there's at most one infinite cluster, right? Because if you had multiple infinite clusters, then you would, by some insertion tolerance, finite energy type argument, you would have edges that have distinct infinite clusters on their two sides. Okay, so this is like a quantitative version of uniqueness. So the thing we'll be using is a version of the same inequality, which I came up with. And the main differences between this new inequality, which I call the Two Ghost Inequality for reasons that may become more apparent in a minute, is that, well, first of all, it's much more general. So it applies to any unimodular transitive graph. And secondly, it works directly with volumes of clusters instead of radii. Okay, so as a result, it's actually stronger than the original Newton. Okay. And what it says is, so for each edge E, define this event SEN to be the event that the endpoints of E belong to distinct clusters, and both these clusters are big in the sense of, so it's convenient for this inequality to measure the volume in terms of the number of edges that you touch. So where we say that a set of vertices touches an edge if it has at least one of the endpoints of the edge. So I want to touch at least n, both of these clusters to touch at least n edges, and I also need at least one of the two clusters to be finite. Okay. So what the inequality says is that if you sum over edges adjacent to the origin, these probabilities, then it's bounded by a universal constant, 6 without the work, times the degree of the origin, multiplied by the square root of 1 minus p over p root n. Okay, so for most purposes we're interested in, the point is this is basically 1 over root n. So unsum unexisting stuff. Okay. So one thing to notice is that this condition that at least one of the clusters is finite should reassure you that this does not prove uniqueness in settings where we shouldn't have uniqueness. Like, so it doesn't follow in the non-amenable case that you have a unique cluster, because you need at least one of these clusters to be finite in the definition of this event. Okay, so this is, even though the original Eisenman-Kester-Newman thing was really about proving uniqueness, here we actually have a version of it which is stronger in some senses, but also doesn't prove uniqueness. Okay, and having said that, in the amenable case, it is possible to remove this condition that at least one of them is finite and get a proof of uniqueness via this method. Okay, good. So, so the proof of this is going to use what's called the ghost field. So, what do I mean by that? So we take our percolation configuration, and then independently we sample a ghost field on the edges of intensity H. So what that means is we just take a random subset of the edge set, independent of percolation configuration, in which each I forgot to write the English probability 1 minus e to the minus h, which is roughly h. Okay, so each edge is included with probability 1 minus e to the minus h. Okay. And we call the joint law of the percolation configuration and the ghost field by e sub p comma h. Okay, and so ghost fields, and I should say that ghost fields are usually done on the vertices, but it turns out to be convenient for various reasons to do it on the edges in this proof. But the point is, ghost fields let us convert questions about the distribution of the volume. That to be a really useful trick that comes up a lot in many arguments in percolation. And it was first used, as far as I know, in
Tom, are you there? I think we have lost him for a minute, so. Yeah, he's back.
Hi, sorry, I'm not sure what happened there.
Yeah, we lost you for a minute, so maybe you could just recap what you said for the last 1 minute or so.
I'm just overhearing my partner in the other room. It sounds like her internet connection as well, so I guess it's just me. Okay, when was
yeah,
I
so
already,
how ghost fields lets us convert questions about
okay.
the volume to the connectivity, that bit. So maybe you can
Okay,
start.
great. Yeah, so roughly what you expect is that at criticality, the easiest way to connect to the ghost field is just to have a cluster of size of order 1 over h. Right? If you have a cluster of size order 1 over h, then you have a constant probability being connected, constant conditional probability of being connected to the ghost field. Okay. Actually, below criticality, that's not true. The easiest way to connect to the ghost field is just to get lucky and just very near the origin of the ghost field. Okay. But roughly speaking, at criticality, you expect connecting the ghost of intensity H should be roughly the same kind of events as having a cluster of size 1 over. And although this Eisenman-Heston-Newman stuff is actually applying uniformly for all P, it's only going to be sharp in the critical case, so we can kind of imagine we're in a critical case. That's very interesting things happen. Good, and of course, really one way of thinking about this ghost field stuff is it's really just a way of thinking about the Laplace transform, the distribution of the volume within a kind of holistic. And So in order to prove the two ghost inequalities I just stated here, really what we prove is this variation on it, where instead of looking at this event SEN that I had before, I'm going to look at this event TE, which will also depend on the ghost. It will be the event that the two endpoints of E belong to distinct infinite clusters, at least one of which is finite, and they both touch at least one ghost length, which could be the same one between the two clusters. Okay? And what we'll prove is that this is bounded, again, some universal constant, but now instead of 1 over n inside the square root, we get h. Okay? And once you have this inequality, you can deduce the original version of the theorem from it, by a totally elementary calculation, just by using the probability of this event defined in terms of the ghost is always at least, well, if this event S holds, then the volumes are both large, so you have a reasonably good probability of getting a ghost, at least when the parameters are tuned correctly. But you get 1 minus e to the minus hn, and then squared because there's two clusters. So, if you use this inequality, you upper bound this probability using this theorem, and then you optimize over the choice of h, and basically just take h1 over n, then you get the inequality that was written before. Okay. And again, really the benefit of this ghost thing is it actually makes it more similar to the original Eisenman Kester-Newman thing. So there, they wanted to look at connections to the boundary of the box. Now we're looking at connections to the ghost, like the set of ghost vertices. But actually, because it's, again, kind of formulated as a connection event, it's actually not that different, even though now we're looking at the volume instead of the radius. Okay. So, so let me now start explaining how the proof is going to be. So, an important thing in this proof is going to be what we call the fluctuation of the cluster. So, in general, if I give you some subgraph, some finite subgraph of G, we define the fluctuation of this subgraph HP of H to be P times this quantity, which is the number of edges that touch but do not belong to H, right? But just to be clear, H is really a subgraph, not a set of vertices. So it's possible for edges in the set have both endpoints in H, but just not belong to H. Minus 1 minus P times the number of edges that do belong to H. And the fluctuation of the cluster at the origin turns out to be a really natural and important quantity for many things in calculation. So in particular, if we explore the cluster at the origin one edge at a time, so we already saw something like this earlier on. So you fix an enumeration of the edge set, and then, so before we were doing things in a slightly more clever way where you only reveal a spanning tree of the cluster at the origin, but now we'll just do it in the more obvious way where you just, at each step, you look at all the edges which are touching the part of the cluster that you've revealed so far, that you haven't already looked at, and then you look at that. So if you do this, then and you keep track of kind of the running version of this quantity, so you have P times the number of closed edges that you've revealed minus 1 minus P times the number of open edges that you've revealed up to time n. Then this is a martingale. So in particular, it's just a random walk on the real numbers with IID mean zero increments, right? These factors of P and 1 minus P are exactly what you need to make it mean zero. And it's just a random walk, and you can compute the cluster at the origin in terms of it, and then you stop the random walk when you explored the whole cluster, if it's finite. Otherwise, this will just come from. And so again, this is a martingale that's kind of stopped when you explore the cluster, and the fluctuation of the cluster is exactly the final value of this martingale. So just as an aside, so I won't actually be using this, but this is one of the main reasons why the fluctuation is important in other contexts, is that taking expectations against the fluctuation lets you differentiate functions of the origin. So if you have if you have some function on subgraphs of G, like the volume or whatever, the square of the volume, the radius, whatever you want, and you look at the derivative of the expectation of that function, well, you can always expand this expectation out as the sum of all possible clusters of the origin times the probability that that cluster is the cluster of the origin, which is p to the number of open edges in the cluster, 1 minus p to the number of closed edges touching the cluster, right, times the function evaluated there. And if you just differentiate this term by term, which of course, you're going to need some assumptions in order for that to be a legitimate thing to do. But if you do differentiate it term by term, and then you see what you get, it's exactly up to this uninteresting prefactor. It's the expectation of f multiplied by the fluctuation. Okay, so well, this is really just something about differentiating functions of IID really random variables, that you get this fluctuation inside the expectation. Okay. And this, so by the way, this is obviously equivalent to Rousseau's formula, but it's not obviously equivalent. And the fact that you have these two different expressions for the derivative be useful sometimes. Anyway, so this derivative formula makes the fluctuation a natural important quantity. So we won't actually be using this, but I think this is kind of related to how Eisenman, Kess, and Newman might have. Okay, so for this Eisenman, Kess, and Newman thing, the key lemma is going to be, so we want to relate the probability of this two ghost event, where we have these two big finite clusters, into something in terms of the fluctuation. Okay, so this is the precise inequality we're going to prove, that the sum around edges incident to the origin of the probability of TE is bounded by an uninteresting prefactor times the expectation of the absolute value of the fluctuation divided by, so this EK0, EK0, this just means this is the set of edges touching the cluster of the origin. We divide by the size of that, and then multiplied by the indicator that the cluster of the origin is finite and it intersects the ghost. Okay, and of course, what I could have done is replace this, right? If I condition on the cluster of the origin, then the conditional probability you intersect the ghost is just 1 minus e to the minus h, and this number of edges. So this right-hand side can also be expressed in terms of just this multiplying by this exponential, and then you don't have to actually have the ghost considered explicitly anymore. Okay. So this lemma is really the magic of the argument. It relies on like a clever trick, basically, where you find a way of re-expressing this probability, and then you do a mass transport, and everything is just slightly magical. Okay, so before we do that, I just need to say a bit more about mass transport principles. So remember, we said before that one way you can define what it means for a transitive graph to be unimodular is that it satisfies the mass transport principle, which says that if you take any function on pairs of vertices to non-negative numbers, which is diagonally invariant, meaning if you shift both vertices by the same automorphism, it doesn't change the value of the function, then fixing the first vertex and summing over the second one gives you the same number as fixing the second vertex and summing over the first one. Okay. Now, there are lots of variations on this equality. So in particular, one thing you can do is have a version of this for functions which are indexed by oriented edges instead of vertices. Okay, and of course this says exactly the same thing, but where I have functions defined on oriented edges instead of vertices. Okay, and you can deduce this edge version of the mass transport principle from the vertex version by just considering the vertex function whose values are just the sum of oriented edges emanating from those two vertices. And then you deduce the in fact, for this proof, we're going to want to do something a bit stronger, which is to use the mass transport principle for a function which is actually signed, so it can take both positive and negative values. Okay, and it turns out that that is a perfectly legitimate thing to do, provided that you have this absolute integrability condition. Okay, so if our function is now to R instead of the non-negatives, but it has this property that summing the absolute value gives you a finite number, where again you're fixing the origin, so you're summing over this coordinates in edges incident to the origin. The second one is over all edges, and of course it's the same as if I did it the other way around by mass transport principle. If this is finite, then the principle still holds. This is easy to see. You just have to apply the usual version of the mass transport principle to the positive and negative parts of this function separately, and you're going to get finite numbers in both cases, so it's fine to subtract them from each other. Okay. Good. Okay, so let's now try to prove this key lemma. Okay, so remember, we're looking at this event TE. Right, which is the event that at least one of these two clusters is finite, and they both touch a ghost. Okay, so it's going to be useful to introduce a couple of more events, and so we'll define FE to be the event that every cluster touching E is finite, and GE to be the event that there exists a finite cluster touching both E and the ghost. I realized in my paper, this is a script G and this is a calligraphic G, which are not really distinguishable in my handwriting, so I'm going to write the ghost field calligraphic G in green so that you can distinguish it more easily. So as I said, it's going to be a kind of a combinatorial trick where we mess around with things and magically this, what we want is going to pop out. So the starting point of this trick is to do this kind of inclusion-exclusion type thing, where we say, let's look at this event, the intersection of TE and FE. So this is the event that these two clusters are distinct, they're both finite, and they both touch the ghost. Okay. So what we claim is that we can write the indicator function of this as the indicator function that the E is closed times this number of finite clusters touching both E and the ghost, minus this indicator function that E is closed, and this event holds that there exists a finite cluster touching both E and the ghost. Okay, and why is this true? Well, this is just something you kind of check by case analysis. So, for example, if if this event does hold, so if we have two distinct clusters that are both finite and both touch the ghost, then here we must get 1, here we must get 2, and here we must get 1, so we get 1. 2 minus 1 is 1, just as we want. If one of the two clusters is infinite, but they both touch the ghost, then they're distinct, then you get 1, here you get 1, and here you get 1, so you get 0. Okay, and you just check all these cases and you see that this is a valid. Okay? And this is really the starting trick that's going to make everything work. Okay. Yeah, similarly, if you only had one, if the clusters were distinct but only one of them touched the ghost, then again you get 1 minus 1. That's just one. And there's, like, I guess, more cases as well. Okay, so let's take this equality, and this is just a pointwise equality, but we can clearly take expectations. So we get that the probability of this event is equal to the expected number of finite clusters touching E in the ghost, times the indicator that E is closed, minus, and then I'm going to split this event up into two further events, the one where this holds and both clusters touching the origin, touching E are finite, and finally the one where this holds, but at least one of the two clusters is infinite. Okay. Now what we observe is that if I look at this event and this one, right, these are disjoints because, well, just trivially, because I have an intersection with this and minus this here. But also their union is equal to the whole event T, right? The one that I'm interested in, that I have both clusters touching the ghost, and at least one of them is finite. Okay. They're not exactly equal, but they're equal up to a null set, because you might have that you have an infinite cluster that doesn't touch the ghost. I mean, this has probability 0, but that would be the set where that happens would be in the symmetric difference of this union, right? Because well, either T holds and this holds, in which case you're in this set trivially, or T holds and you have one of the two clusters is infinite, and then that infinite cluster must touch the ghost just trivially. Yeah, sorry. T holds, so it does touch the ghost, right? If you're anyway, I'm getting confused here, but this is just a trivial thing as well. Okay, so what that means is we can move this probability over on the left-hand side, and we get just this probability that we're interested in. Okay, so we get that the probability that we're interested in is this expectation of the number of finite clusters touching E in the ghost, the indicator that E is closed, minus this probability. Right? So again, this is the probability that E is closed, and GE is the event that there exists a finite cluster touching E in the ghost, and this is the event that both clusters are finite. Now, the nice thing that happens here is that actually the status of E is actually independent of this event, the intersection of G and F, right? Because whether or not E is closed doesn't affect whether or not this event holds, right? If I have both clusters touching the E are finite, that certainly doesn't depend on whether or not E is open or closed, right? Because I just need these, whatever I can reach from both sides needs to be finite. And then, given that that happens, it also doesn't affect whether G holds or not, whether E is open or closed. Okay, so because the status of E is independent, I can change this condition that E is closed to the condition that E is open at the cost of this factor 1 minus P over P. Okay? And in fact, once you've done that, this intersection here becomes redundant because this intersection, right, that E is open and there exists a finite cluster touching E in the ghost. Well, if E is open, then the two clusters must be the same, so they must both be finite, and then it's trivially inside this event, so I can now ignore it. Okay, so the upshot of all this is, and I can rewrite this in a slightly different way, that the probability of this event is equal to the expectation of the number of finite clusters touching both E and the ghost, right, so this either 0, 1, or 2, multiplied by this factor, which is, it's going to start looking a bit like the fluctuation, right? So I have the indicator that E is closed from here, and then I have minus 1 minus P over P, the indicator that E is open. Okay, so these two lines are just rewriting the same thing in a more explicit way. Okay, and just to be clear, at this point in the argument, we haven't used anything about the graph. This is true on any graph, right, and any edge E, right? We haven't used anything about the symmetry of the graph. Okay? But now, at this stage, we want to use that we have transitivity and unimodularity to take this quantity on the right-hand side, apply the mass transport principle to it, and get that thing expressed in terms of the fluctuation of the cluster of divergence. So basically, we want to take this quantity kind of average it out over the cluster at the origin, and that will give us the what we want. Okay, so how are we going to do this? So we're going to define a function. So it's convenient to use oriented edges, but we'll always use the convention that if I have some function defined on unoriented edges and I plug an oriented edge into it, I just evaluate it on the associated. So I'll define the function as follows. So f of E1, E2 is going to be the expectation of this sum. So it's convenient basically in order to avoid writing like a massive thing in the subscript here. We'll use this notation summing over a set like this to just mean this more. Okay, it will sum over clusters, finite clusters touching both E1, E2, and the Ghosh field of this quantity. So the indicator E1 is closed, minus 1 minus P over P, the indicator E is open, divided by twice the number of edges that the cluster touches. And just to be clear, although we're doing things oriented, this touching relation is something really about unoriented edges, so it doesn't matter whether you're starting to your endpoint. And that's why we multiply by a factor of 2 here, because there's just 2 orientations for each. Okay, and so the first thing to notice is that this multi-set that we're summing over, where it has size at most 2, right, 0, 1, or 2, and from there you can easily see that if you have the integrability conditions you need to apply the mass transport principle of this function, which is be both positive and negative. Okay, so this is something that's easy to check. You just take the absolute values and blah blah blah. You just check that this is just at most constant. Okay, I guess it's at most 2 times 1 minus 1 over P over P. Okay, so we have the integrability we need to apply some mass transport. Now, if you look at the sum of these probabilities of the event that we're interested in, right? Well, obviously we can use this formula and express this as the sum of these expectations. But by the way we've defined this function, that's just exactly equal to this, right? Because when I fix E1 and sum over E2, right? When I sum over E2 in this quantity, I just get, you know, there are 2 times the number of edges this cluster touches that are relevant here and get summed over, and I sum the same thing for each one. So that number of things I'm summing over just cancels with this denominator, and I just get this quantity that I started with up here. Okay, so now what I can do is apply the sign mass transport principle and flip the order of these 2 numbers, these 2 edges, sorry. Okay, and if you do that, so now E1 is just being summed over edges emanating from the origin, but E2 is summed over all edges. And if you look at what you get here, it's going to be exactly this quantity. So 1 over P times, right, so times the sum of the over clusters, finite clusters touching E1 and the Ghosh, the fluctuation divided by the volume. Okay, so again, this is something you can just kind of check by staring at it for a minute. So the 1 over P is going to come because the fluctuation we defined as P times the number of closed edges minus 1 minus P over P. Sorry, times 1 minus P at the open edges, whereas here we don't have the P here, we have a denominator here, so you get 2 minus P. And then, you know, you're just summing up, you're fixing the second coordinate and summing over the first one, so you're summing over all these difference of indicator functions, and this is exactly giving you the fluctuation. Okay. So now what you can do is just think about it for a minute and say, well, I have this slightly annoying thing where the number of things that I'm summing over is random. But if you include an absolute value here, then you can stop worrying about that and just say, well, it's at most the sum of the cluster at one endpoint and the cluster at the other endpoint, then you get via some easy considerations that this is bounded by 2 of p. So 2 is coming from the fact that you have at most 2 things in the sum here for each edge, times the number of edges you're summing over, times the expectation of the ratio of the fluctuation to the volume on this indicator. So now you're looking at the cluster of the origin on this indicator that it's finite and it touches the ghost. Okay? So, there's a little bit of justification you need to do to get this, but it's basically good. So this establishes the key lemma, okay, which again, it's relating the probability of the event that we care about to this expectation, which involves the ratio of the fluctuation to the volume. Okay, and now we want to conclude the proof. We want to bound that expectation using martingale methods. Okay, so as we discussed before, if you explore the cluster of the origin one edge at a time and you keep track of like the running version of this, where you have p times the number of revealed closed edges minus 1 minus p number of revealed open edges, this is a martingale, and the time where you've explored the whole cluster is the stopping time. Okay, and we're going to right. This might be infinite, but if it's finite, then it's finite. Okay, and ZT is, so if the final value of this martingale when it stops is just equal to the fluctuation of the origin. Okay. So if you take this lemma that we just proved and rewrite it in terms of this martingale, which again is a very simple martingale, it's just a ID random walk on the reals that's just stopped at some time. Then you get that it's the expectation of absolute value of z of t over t times this 1 minus e to the minus ht. It times the indicator that t is time. Okay. And so to conclude the proof, we want to prove basically that this is bounded by a constant times square root of h. Okay. And this is really just going to be martingale analysis now, nothing to do with percolation anymore. Okay, and hopefully this is plausible that it should be this order, because kind of what's going on here is that, if you like, in order for the cluster of the origin to touch the ghost, it should get to size 1 over h. Okay, roughly speaking. Let's just talk heuristics at this point. Now, so that means that this martingale is running for order 1 over h steps. Okay, but if you have a martingale and you run it for n steps, right, indeed it's just a random walk, right? Then you expect it to have size about root n, right? So what you're roughly thinking is that what's going to contribute to this expectation is when t is of order 1 over h, and z of t is going to be of order 1 over root h. Okay, and then you multiply these things together and you should get this root h found. Okay, and so the way Eisenman, Kessler, and Newman did this in their original analysis, they used like large deviations type calculations, and that's why they got this extra log. What we'll do instead is a slightly better way where you use maximal inequalities, and then you don't get any additional log factors. Not that those log factors are very important for most applications, but this is not necessary. Okay, so what we do is, to bound this expectation, is we break it up into sums over dyadic scales. Right, and the point there is that we can bound, so if t is between 2 to the k and 2 to the k plus 1, right, well, then we can bound this by 2 to the k and this by, right, I mean, this function 1 minus e to the minus hx over x is is decreasing, I guess. And anyway, this lets you pull out this factor as if it's at the bottom, if t is at the bottom of this dyadic snare. Okay, so you get this, and then to bound this expectation, you just use Dub's maximum equality. So Zn is martingale with and its increments have this variance p1 times 1 minus p. So you get that the whole second moment of Zn is bounded by p1 minus p times n. And then you use Dub's maximum equality. You learn that the expectation of the square of z over this dyadic interval is at most 4 times the expectation of z at the end of the interval, right? This is exactly what Dub's maximum equality tells you, right? So then you just put these bounds together, and you use Jensen to bound this. So you get that this expectation is at most the sum over dyadic scales of the same thing we had before, and this thing that's basically 2 to the root 2 to the k. Okay. And from here, it's just calculus to show that this holds. This is this sum that you get here is just at most constant under root a. Okay, and I won't go into this because it's not particularly interesting. Just we bound the numerator by 1 minus e to the minus h 2 to the k is always at most h times 2 to the k, right? And use this bound for the small k, and then the trivial bound that it's at most 1 for large k, and then you just get some geometric series coming in and you estimate them. This is all pretty easy stuff. Just not going into everything. And this completes the proof. Okay, so again, what have we done? We took this probability that we're looking at the probability of like these two large clusters, and we did this mass transport argument, which is basically exchanging the order of summation somehow to transform this into something about the ratio of a martingale run up to some stopping time divided by the stopping time, and then we used classical techniques in martingale analysis like Dub's inequality to analyze this expectation. Okay. So that completes the proof. So what we want to do now is somehow use this two ghost inequality, which is saying that it's difficult to have two large clusters that are next to each other. And we want to learn that we want to use this to prove this theorem that says that you have power law upper bounds on the volume of clusters at criticality. Okay. So somehow we want to go from knowing that it's hard to have two large clusters close to each other to knowing that it's actually difficult just to have one large cluster. Okay. And in the exponential growth case, this is something that is relatively easy compared with some other cases where you can do this, because we already know that connection probabilities are decaying, right? Because we proved that before, right? That for any n, I can find 2 points within distance n where the connection probability at criticality is exponentially smaller than n, right? And that's the growth to the minus n. So let's try and do this proof. So the first thing that it's going to be useful for us to use is, so the two ghost inequality tells us that it's hard to have two large clusters that are like right next to each other. Right? Like I take an edge and I want its two endpoints to be in distinct large clusters. Okay? So the first thing we're going to want to do is have a lemma that lets us have these clusters a bit further away from each other at some cost that depends on the distance. Okay, so the precise inequality that we prove is that if you have 2 points, the origin and x, that are some distance from each other, then the probability that the origin and x lie in distinct clusters, both of which have size at least n, is at most this probability we get control of from the two ghost inequality, namely the same thing but where the origin and x are neighbors, so you're supremized over all pairs of neighbors. multiplied by something which is basically p to the minus the distance. Okay? So saying that, you know, if we take origin next not too far away from each other, then we're still going to get useful bounds from the two distance. So why is this true? So I'll just tell you the sketch, which is that if you start with this event that the origin and x are in two distinct large clusters, consider the geodesic between the origin and x just in the ambient graph, and think about like forcing the edges of this geodesic to be open one at a time in order from the origin to x. Okay? So of course, once you force all these edges in the geodesic to be open, you must have actually merged these two clusters, right? Trivially. So there must be some last time when you're just about to merge them, right? And at this step of the process, you have this edge, the next edge you're going to add, which is going to merge these two clusters. So it must have the property that it's two endpoints, both, I mean, basically that this event S holds, but on this modified configuration where you've been forcing a bunch of edges to be open. Okay, and so by doing this surgery, we're forcing this event SE and to happen at some choice of E. And then to prove the inequality, you just have to keep track of, you know, what is the cost of doing this surgery. Basically, the worst thing that can happen is you have to force all these edges to be in, which happens with this probability minus the distance. Okay, and you know you have to do a little bit of work to make this completely rigorous and precise, but that's basically the intuitive reason. So I should say that there's also this issue that you're causing this event to hold like a random edge instead of a specific one, and this also causes some problems. It makes this thing worse. It's basically where this factor 1 minus p comes from here. So it's not actually that bad in this particular setting. Okay. So now we have a way of saying that it's hard to have two large clusters that are kind of moderately close to each other. Okay, so in particular, you know, we know that this guy here is bounded by constants over root n, right? So in particular, if the distance is only like logarithmically small with a small constant, then this is still going to be like 1 over our event to have these two big clusters logarithmically close to each other. Okay, so what's the next step? So let's look at, so what we're going to do is take the origin and x to be two vertices, and we'll look at this event that both of their clusters are large. Now these, so I'm not requiring them to be distinct in this event. Okay, so this is just the intersection of the event that the cluster of the origin is large and the cluster of x is large. These are both increasing events, they're positively correlated, so I can bound this below by the square. Now on the other hand, I also have by union bound that the probability both these clusters are large is bounded by the probability that they're large and distinct, plus the probability that they're not distinct, the origin and x are connected to each other. Okay, just trivially, I mean, this event is contained in the union of these two events. Okay, so if we use this surgery argument we just saw together with the two ghost inequality to bound this first event, right? And then we infamize over the choice of x in the second thing, what we get is for each distance r, this squared tail probability is bounded by basically p to the minus r times this two ghost event, the probability of that, plus this kappa p of r, which remember we defined to be the infemal connection probability in two vertices at distance of most r. So if we use the two ghost inequality to bound the first event and this thing we proved last time to bound the second thing, we get that this square is at most this, right? P to the minus r over root 10 times the growth to the minus r. Okay, so at this point you're done. You just take r to be a small constant times log n, and you get that this is so that this term beats this term basically, and you'll get that the right-hand side is bounded by some negative, and then you just square root the size and you're done. Okay. So that's the whole proof. Okay, and you know, if you do things carefully, you'll see that all the constants, as I said before, they only depend on the degree and on width. Okay, cool. So this argument that I was just explaining to you was the first in what's now a series of a few papers where I've used variations on the same argument to prove various things. So the first subsequent thing was this work with Jonathan Herman, where we used a variation on this to prove that there's no percolation on a PC for certain groups of intermediate volume growth. So they have sub-exponential but super polynomial volume. Although, you know, it remains open to prove there's no percolation in PC for all such groups, including some of the most well-known examples. Then more recently, I've used variations on the same thing to prove continuity of the phase transition for the Ising model on non-amenable groups. And again, you get all these parallel type bounds as well, which is nice. And then even more recently, using this to show parallel bounds for critical long-range percolation, ZD. And it seems like, you know, there's certainly scope for more things to be proven using these ideas. Really the place where, so there are kind of two things you need to do to get these kind of arguments to work. You need a way of efficiently converting volume tail bounds into bounds on connection probabilities. And that's actually something, for example, on ZD, we know how to do basically as well as possible. So that's something where there doesn't seem to be much room for additional improvement in optimization in the arguments. The thing that's has a lot more room for optimization is in this surgery type thing, where we want to get bounds on the probability of having two large clusters that are, instead of being next to each other, they're at some small distance from each other. And the dependence on the distance here is really bad. And this is something where I think there's a lot more scope for improvement, particularly if you want to try and attack nearest neighbor models on ZD or something like that. I can say more about this later, maybe. In the remaining time, I wanted to maybe explain some of the ideas in this paper with Jonathan, where we showed there's no percolation of PC on some groups of intermediate volume growth. And this will give you a better idea of how this sort of argument works in a more difficult setting, and then I can say more about the challenges on ZD. So the precise theorem we prove is that if you have a transitive unimodular graph where the return probabilities for random walk decay sufficiently quickly, so we want them to be at least e to the minus a power of n, where the power is strictly bigger than a half. Okay, so under that condition, we prove that there's no percolation of criticality on G. Okay. And this applies to some groups of intermediate growth. For example, Anna Oeschler has this construction of what she calls piecewise automatic groups. And what these are good for is that they show that you can construct groups of intermediate growth where there's return probabilities decay arbitrarily quickly, provided that it's sub-exponential, right? So we know that non-amenability is equivalent to exponential decay of return probabilities. But what Oeschler's construction shows is that if you just want something close to being exponential decay, like e to the minus n over log n, whatever you want, anything sub-exponential, you can find a group that has sub-exponential volume growth, but satisfies that return probability decay condition. So in particular, you certainly have groups of intermediate growth with this fast, with the stretched exponential return probability decay with large exponents. And So of course, if you look back at what we just did in the exponential growth case, it was really important to us that we had this bound on kappa p of r, right? This minimal connection probability at distance r. Right? So we actually proved that via a completely unrelated method, right? And then fed it into this Two Ghost stuff to get the bound. And obviously that's not going to be a method that's available to us now because we don't have an a priori bound on these connection probabilities. Indeed, if we had such a bound, we would already be done because that implies that there's not a unique cluster at PC, and because we're in the amenable setting now, but that just means so we're going to need to do something different. And the idea is to use a bootstrapping method. So this is a general approach that you can try to take to prove that there's no percolation and criticality. And the way it works basically is you take some assumed bound on the distribution of the volume of a cluster, which you call the bootstrap analysis, and you want this to be a bound that trivially holds when p is very small. And then what you want to do is show that this assumed bound, the bootstrapping hypothesis, actually implies a stronger version of itself. Okay, so that might seem like a silly thing to do, but if you can do that, then what you're going to deduce via a continuity argument is that the strong form of the bound holds uniformly all the way up to PC, and therefore it must hold at PC as well, and then you're done. Okay, so so a classic example of this kind of argument is that in high dimensional percolation on ZD, what Hara and Slade did is more or less they showed that if you're on ZD with D very large and the 2-point functions, the connection probabilities for percolation, if they're always bounded by 3 times the Green's function, then actually they must always be bounded by 2 times the Green's function. Okay? And if you can prove such an implication, with this constant becoming smaller, you can actually deduce by continuity that the strong form with the smaller constant is going to hold uniformly all the way up to PC. Basically, because if it started to fail to hold, well, you'd still be above you'd still be bounded with the larger constant, and then the implication would say that, oh, you're actually bounded with the smaller constant, so you get a contradiction. So it's just this simple continuity. And what we want to do is something similar here, where we want to basically start with an assumed bound on the tail of the volume. Then we have to find some way to obtain a bound on these minimal connection probabilities, okay, which is going to be something new that we haven't already done. We'll do this using random walk analysis. And then, well, the argument we've just seen gives us a way of converting bounds on these minimal connection probabilities into volume tail bounds, right? I mean, the specific inequality we proved basically was that the square of the volume tail is bounded by p to the minus r over root 10 plus p of r, and then you optimize over r and you get this volume tail. Okay? So what we want to do is kind of start with an assumed bound on the volume tail, obtain a bound on the minimum connection probabilities, and then get a new bound on the volume tail via this inequality. And hopefully what happens is we actually get a stronger bound than the one we started with. Okay? And if you can do that successfully, then you're going to prove that there's no percolation PC. So as I said, we're going to try to do this. We're going to bound minimum connection probabilities by bounding connection probabilities between 2 points of a random walk. Okay, so let's suppose I take my percolation with p less than pc, so all the clusters are finite, and I take an independent random walk. Then I want to look at the probability x0 is connected to xk, and obviously this is an upper bound on p of k. Right, because there's 2 points have distance almost k from each one. Well, I can write this out what it is. It's the sum over the vertices in the cluster, or the expectation, the sum over the vertices in the cluster, that the random walk is at that vertex at time k, which is just this. So what I can do next is maybe seems a bit silly, but I can introduce an extra variable y and just sum over something that just sums to 1, sum over y. So the sum over y, the indicator that y belongs to the cluster of the origin divided by the volume of the cluster of the origin. Then these two things are trivially equal. Okay. But now what I can do is I can apply the mass transport principle to switch the roles of the origin and y. And what I get is that I get the expectation of the sum over y, sum over x belongs to the cluster of y now. The indicator, so I'm just swapping all the origins and all the y's. Right? The origin belongs to the cluster of y, over the cluster of y, that's this position probability. Okay. But now the point is that, if the origin belongs to the cluster of y, then that's the same as y belongs to the cluster of the origin, right? So I can change these back to the way I had them around before, and I get in the end that this is equal to the expectation of 1 over the volume of the cluster of the origin times the sum of all pairs of points in the cluster of the transition probability, which I can write in my L2 notation like this. Now, before going further in this intermediate growth kind of setup, let's just notice that something very nice happens here if the graph is non-amenable, which is that this inner product, well, I can pull out the norm of p to the k, which is the spectral radius to k, which remember is the spectral radius is strictly less than 1 when the graph's non-amenable by Keston's theorem. And I get the spectral radius to k times the volume k, right, which cancels with this. Okay, so what I get is that the probability that the origin is connected to xk is always bounded by the spectral radius to the power k, and p is less than pc. Because this bound holds uniformly all the way up to pc, it must hold at pc as well, because as we saw before, connection probabilities are always left continuous in p. And this estimate that you get, saying that the connection probabilities are always bounded by the spectral radius to k, is known as Schramm's lemma, though Schramm actually had a completely different proof of it. One thing to notice here as well is that this proof is really general, because it doesn't actually use anything to do with Bernoulli calculation. It works for any automorphism invariant population model with no infinite components. So the probability of any such model on a non-amenable group, then you must have this decay of connection probabilities with the spectral radius to the power. Okay, and of course you can use this bound to give an alternative proof of this parallel bound that I was explaining before. Now this is really nice, but the problem is that if we want to do something similar in an amenable setting, it's not going to work as nicely as this. So what happens is that in the non-amenable setting, this quantity here, so the inner product divided by the volume, is small uniformly in what this set is. So if you take any finite set, this is going to be bounded by the spectral radius to k, so it's small. If k is large, then it's small uniformly in the choice of this set A. But that's just not going to be true in the amenable case, because I could take A to be like one of these like Fallner sets that has that most of the points of A are deep inside it and not near the boundary. Of course, if I take a set like that, then this quantity here, well, it's really just the same thing as I've written here. It's the probability if I start a random walk at a uniform point of A that's in A after k steps, right? And if I take one of these Fallner sets where most of the points are deep inside, then of course this is going to be close to 1, even if A is very large. So I can't hope for this uniform control independent of the set A. Okay? But what does happen is that in this setting that we're looking at, where the return probabilities don't decay exponentially, so it's amenable, but they almost decay exponentially with the stretched exponential with the good exponents, then this quantity, it does depend on A, but in a very mild way. Right? So the specific inequality we prove is that this quantity, which again is the probability that if you start a random walk at a uniform point of A, then it belongs to K after A steps. This is going to be bounded by something in this form where I have e to the minus minimum of K over this power of the log of the volume and K to the gamma. Okay. So again, the point is that this does depend on the set, but only in this really mild way. Right? So if gamma is close to 1, this is like we're getting this log to a small power of the volume inside. So this is a very mild dependence on the size of it. Okay. So what you can do so this is just for arbitrary sets, and if we take this equality that we had before, expressing this connection probability in terms of this expectation, plug this inequality in, and of course we just get this inequality. And if you do a bit of calculus, you can convert this into something that's a bit simpler to work with, which is that the connection probability is bounded by, so for any beta between 0 and 1, you get the expectation of e to the log to the beta of the volume times e to the minus k to some this power beta times gamma minus beta. Okay, which we'll call this alpha. Okay. Now this is, this gets pretty computational, but the point is that if gamma is bigger than a half, then you can find a value of beta where this exponent is bigger than beta. Okay, and why is this useful? Well, again, this is a bound on kappa p of r. So if I plug that into this inequality I had before, I get that the volume tail squared is at most this thing from the two ghost inequality plus this quantity here, right? Where I get this. And the point is really that this e to the log beta, the cluster volume, this is a very small thing, right? I mean, e to the log to the beta of x with beta less than 1 is a very slow growing function. Right? It grows slower than any polynomials. And here I get e to the minus k of alpha, where alpha is strictly larger than beta. Okay, so again, this is probably not the easiest thing to follow at home, but if you just do a bit of calculus, so if you rearrange this, I mean, you take k to be a small constant times log n. This term is just going to be negligible compared with this term if you set it up right, and you get that this tail probability is bounded by basically the square root of this times this e to the minus log n to the alpha. Okay. And what you can then do is sum up these tail probabilities in the right way to compute this expectation, right? And you get, after a calculation, basically because alpha is bigger than beta, you get that the expectation of this e to the log beta of the cluster volume is bounded by the square root of itself times constant. And then what you do is you rearrange, you find that, which you can do safely because you're below PC, you know that the cluster of the origin has a finite expected size. So in particular, this small thing must certainly have finite expectation as well. So everything's finite. You can safely rearrange this. You get that this expectation is bounded by some constant, and this constant doesn't depend on P, right? So this bound, again, must hold uniformly all the way up to PC, and therefore at PC itself. Okay, so you're done. You have this expectation is finite at PC, so in particular, the cluster of the origin must be short. So that's the end of the proof. And as I said, if you want to do something like this on ZD, which is of course really interesting, the main thing seems to be that you need to find a much better way of converting this probability of bound on two large clusters near each other to two large clusters that are a bit further away from each other. maybe to get something that remains useful when they're actually polynomially far away from each other in the compared with how large you want the clusters to be, something like that, instead of a block. This is really interesting. The main problem seems to be you need to find some way of like localizing where this edge is going to go. So forcing it to be on the geodetic is good in one way because there's not so many choices of where this edge you're creating is going to be, but it's bad because you pay a lot of probability to force it to occur there. So anyway, this is interesting stuff, and I'd be happy to chat about it more. Well, I'll stop there for today.
All right, so let's thank Tom before taking any questions. Do we have any questions?
I had a question.
Yeah, go ahead. Yes.
So in the last theorem, you proved that about having no clusters at criticality in groups of intermediate growth. The condition on random walks that Pn is bounded by some exponential thing, is that related to, say, the random walk triangle condition? I mean, it seems to imply that, right?
Well, it certainly implies the triangle condition, yeah, but it's I mean, that triangle condition should already hold if the the triangle condition for random walks is equivalent to the return probabilities decaying faster than 1 over n cubed. So so obviously, yeah, I mean, ideally we would say something like, if you have return probability decaying faster than 1 over n cubed, then you have mean field critical behavior. But that seems, totally beyond the realm of what.
Okay. Thanks.
By me, anyway. Yeah, I mean, the specific thing with the gamma being bigger than a half, that seems to just be a kind of technical thing in the proof. I mean, we do argue in the paper that it's not possible to use our method for gamma less than half. So there really is a new idea that's needed, but it's unclear why this half is, or there doesn't seem to be any reason intuitively why it should be important. It's just this method breaks them.
Any other questions? Okay, so if not, then maybe I can ask a couple of questions. So one thing is just following up on the previous question. So you talked about this Oersler's piecewise automatic groups. The most standard example of this intermediate growth group is this Grigorchuk groups, right? So do your results apply for those?
No, no, they don't. So I should say that there are some. We can also prove some slightly stronger things where you instead of only looking at this exponent gamma for the heat kernel decay, you introduce another exponent governing the rate of escape of the random walk. And if these two parameters together satisfy some inequality, then it works. My understanding from talking to the experts is that they don't know whether this inequality is satisfied the Grigorchuk group or not, because the exponents aren't known exactly. I think the answer is that it probably doesn't apply, but it's not really clear. In any case, it would be really interesting to extend this, like, to all, if you just let the gamma as positive, for example, then that would cover all known examples of groups of intermediate growth, and perhaps all examples of groups of intermediate growth, if you believe some of the conjectures that are. That seems to require a new idea.
Okay, thanks. Yeah, and another question, it's from earlier in your talk. So about this Eisenman-Kasten-Newman method. So you said that your two ghost inequality in the amenable setting, you can drop this one cluster being finite assumption, and you can recover a form of Eisenman-Kasten-Newman.
Yeah.
So if I recall correctly, the Eisenman-Kasten-Newman had a log n over square root n, right?
Yeah, but the log n, as I said, it's really just it's an artifact of the way they do the analysis, that they use large deviation things, and they do it in a slightly more coarse way. Basically, if you use you can do the same proof as they did, but if you use maximum inequalities instead of.
Okay, I see. So you actually get the 1 over square root n in the amenable case as well.
Yeah.
Oh, okay. Yeah, that's nice. I see.
In fact, I mean, this thing is really not shot because here we get the volume instead of the radius, so you can you can get really better things than this, because if you do have this event, you can argue that you're not going to get these things aren't just going to be paths; they have to be really bigger than it.
All right. Any further questions? All right. So goodbye for now, and I'll see you guys later. Okay. Thanks, Tom.